Okay. Apologies to the Chicago students. I have a PhD exam today, and I just cannot get back on campus in time if I go up to Chicago. So bear with me, and I'll try to be there next Thursday when we kick off the final project and meet with the Chicago students. We're going to have an exam on Tuesday, okay, next Tuesday. And it's going to be, it's already announced on Piazza, the exact time and location, and the wiki. So it's going to be 6:30 p.m. through 9:30 p.m. The exam shouldn't take full 3 hours, but there are always students who like to double check, triple check, quadruple check the answers. So we don't want to make the exam a matter of rushing you, right? So, we'll give you 3 hours. But you should be able to finish with in about 2 hours to 2.5 hours. Okay, it's going to be exam with 5 parts, and the first part is simple, multiple choice and simple answers, and the rest are going to be more programming-oriented questions. So many of them are going to be similar to the lab questions. So make sure that you really go back to the lab questions and study. And the study guide is going to be very important. The study guide is a little bit out of date because we shifted the topics from later on the semester to the earlier part. So you will need to take that into consideration. I'm going to go through a pass of update about this study guide one more time in the next couple of days. Okay, so watch out for an update to the study guide, and that should also help you to kind of finalize your study over the weekend. Make good use of the TA office hours. The TAs have been telling me that that they don't have much business in their office hours. So take advantage of it. These TAs are extremely experienced. Most of these TAs have been with me for the past 2 years. Okay, so they really know the material. They can help you and so on. So take advantage of it and make sure that you do well. Okay, the exam is really not meant to be any kind of I would say hassle or anything. It's really just to make sure that you study, you understand the material, you have done your programming assignments, and you're solid, so that when you go and interview, when in the future, when these companies ask you these kind of questions, by the way, these questions are often asked by the interviewers, and they can probably say that I took 408, I know exactly what it is. Okay, so make me proud. Okay, so the exam coverage is going to be up to the lecture last Tuesday. Okay, so all the way from lecture 1 to lecture 11. So this is going to be covered in the next exam, right? But so we want to make sure that we give you enough time to study. When you take the exam, as far as the material is concerned, but also still make sure that you pay attention. This course can be very nice if you just keep up with the course. You shouldn't have to spend more than 5-6 hours a week reading through the book chapters, reviewing the lectures and doing the programming assignment. That should be it. And so that should be a very reasonable workload. So don't shortchange this course by spending all your time on 391 or 385 or something, okay, X. And, that's a very bad strategy, okay? That's one of the things that previous students told me, they felt that they can shortchange this course by spending all their time on 374, and then at the end of the semester, oh, I wish I spent a little more time on this course. So don't do that, okay? So we went through the perceptron last time, and we talked about multi-level perceptron. The most important problem that the multi-level perceptron is trying to solve is that a lot of times when you have this data that you want to classify, there's no single line, okay? There's no single line you can use to make that classification. So in this case, when we have this exclusive OR function, we cannot draw a single line that separates the middle ones with the outer ones, right? So that's the fundamental problem we're trying to solve. So if we do an exclusive OR as a linear combination of the n and OR function, there's just no line anywhere we can draw. So this is, the column that we are showing here is just a simple addition of n and OR together. But the line is going to have ambiguity in the middle. So we can't really do a single line, a linear combination of n OR. So that's why we went to the multi-layer approach and added nonlinearity. The nonlinearity is going to be very important because nonlinearity is the main tool for us to reposition data, okay, to reposition data after each stage. So I talked to Carl Pearson after the lecture, and then so we feel that this is one insight that you really have to learn before you start to to work on your neural nets. So here is here is the perceptron formulation. We still have the linear, the two lines, x0 plus x1 minus 0.5 for OR, and then x0 plus x01 minus 1.5 for AND. However, we added that sign function. Sign is SIGN. Okay, it's not SINE. Okay, so SIGN sign function to essentially introduce that nonlinearity, so that we can have +1, -1 out of the the continuous function. So this sign function really adds the nonlinearity to reposition data. Okay, this is a very, very important insight that you need to have when you come to these deep learning kind of networks. Every stage has this nonlinear function at the end, and that nonlinear function really is about taking the linear function of the stage and then do a little bit of a data repositioning. So let's go into this thing. So let's go back to the exclusive OR function. Remember, we have those 4 data points, right? x0, x1, there's 4 combinations. And they are distributed in the space so that we don't have a simple line that we can use to partition, right? So what we do is we apply the first layer. So the first layer gives us the AND and OR, right? AND and OR with that nonlinear, the sign function at the end. So what that effectively does is that, remember, the AND and OR becomes the input to the second layer, right? So you can treat the AND output and OR output as the coordinate, as the x0, x1 in the next layer, right? So the next layer now has the AND output and OR output of the original data points. And if you plot those points, you will see that these two points have been moved together, okay? These 2 points have been moved together. And then those 2 points have been kind of stretched a little bit farther away from each other. And this repositioning here is extremely important because that reposition allows us to now draw a line to separate out those 2 categories, right? So that sign function is really the key for us to be able to move the point into to the other side of the spectrum, so that now we can draw a linear line. And so this is the reason why after every layer of convolution, or every layer of all connected whatsoever, we always add a sigmoid or something similar to that to be able to to carry on by taking something that's initially extremely hard to classify and probably no solution into the kind of repositioned grouping that we can begin to draw nice linear lines. Okay, so this is one of the things that I wish most of the the machine learning classes go through. When I was taking the class, when said, okay, this is what it is. Why don't you just say that? I think some of the machine learning classes probably cover it this way, but some of them I know they don't. So I want to make sure that since we're a computational-oriented class, you need to have the right kind of intuition to be able to fully understand all the computation that we're going to be talking about in the next couple lectures. So now we're good here. So we already covered these things. Okay. So essentially we can scale the input. Okay. So we used to have two x0 and x1 in that little example, but when you have a real world input, you could have a large number of bits, right? So for example, the pixels. The pixels in a picture, each pixel has minimum of 8 bits, right? So so then we have 1,000 pixels, 1,000,000 pixels, and so on. So all those bits become the x0, x1, x2, all the way to maybe even millions of these x's, right? So we also have this output y. Y is the conclusion that we're making. So in that previous example, we use y as the binary decision whether it's true or false, right? Whether it we have a exclusive or true or exclusive or false. So it was a single bit. But in a real application, we could be trying to classify these pixels into 1,000 categories. So 1,000 categories takes, one hot encoding will be 1,000 bits, but you can encode it into these, numbers. So you can encode that into 10 bits. So that will give you either 1,000 bits or 10 bits, depending on how you want the output to be encoded. So Y could be, also a large number of bits. So, the perceptron, the straightforward perceptron, implementation for as a fully connected layer will essentially make every input bit to contribute a value to contribute to every output value, right? So that's where the fully connected layer comes from. You will have a weight going from every input to every output. So you will need to have exactly the number of input times the number of output, number of weights that you can have in the system. And your job in training this layer is to determine those weights, right? And so in reality, it's too tedious to use all single bit input and single bit output. So that's why we typically will treat each one of these as a numerical value, such as the 8-bit pixels. So the 8-bit pixel value will typically come in as an x0, right? So just so that the weight then is going to be a floating point number that will be multiplied to that particular weight. And the rationale is that these 8 bits in the pixel are not totally independent of each other. They all together gives you a particular color, right, of the pixel. So that's why we typically will group them together as a logic unit. So now, for practical networks, you will typically see x0, x1, and so on are pixel values or sound samples and so on, and the ASCII characters, right? So those are the typical input values. Weights are typically floating point numerical values, and then the Y values are still typically the classes, one-hot encoding or a numerical number that gives you the class, that the input belongs to. And oftentimes, we don't just give that value. Oftentimes, we calculate the probability, right? Remember that also. We actually have the network to output the probability of this input belonging to each output category. So in that case, if we have 1,000 categories to classify, we will have the output will be 1,000 probabilities, and hopefully the highest probability one is indeed what the object, what the input is. Okay. So any questions? Any questions? Okay. And then we actually, talk about the multi-layer terminology. We have, the layer that deals directly with the input values are called the input layer, intuitive. And the layer that generates the probability or the classification, that gives you the output is typically called the output layer. And then you have all these intermediate layers. And remember, these intermediate layers are there to deal with these nonlinear, the situation where you cannot draw these linear lines to separate the data. The more mixed up, the more complex your data set is, the more layers you will need in order to kind of keep sorting them into these, reposition them so that you can actually get something reasonable, right? So that's why, we have this terminology called deep learning. Because, oftentimes the real world data is messy, the real world data is not very well, organized. So you need to have many layers so that you keep repositioning the data after each layer so that they become, more separable, right? So that's what deep learning, the intuition of these deep learning techniques are. So if we look at the number of weights, it's very important to understand the weights and biases, right? We need to have these weights and biases in order to draw those lines in each layer. So the number of weights is really the combination, the product of the number of inputs to that layer and the number of outputs from that layer, right? So that's why these things can be very big if we start to look at any of these convolution, high definition image as input, right? And when we start to have many categories of output that we need to classify the objects for. So that these things start to do the product, and then you have these very rapid growth of the number of weights. So in this case, the simple example, we have 4 inputs, and we're going to have 4 outputs in this particular input layer. So the weight is a 4x4 matrix, and the weight is a 4x1, because we just need to have 1 for every output. The bias is 1 per output, right? So, and then the second layer, the hidden layer, has 4x3 because it interfaces to the output layer. So the number of inputs is 4 here, but the number of output is 3. So we have 4x3 matrix, and then the bias is a 3x1 matrix, simply because we only need to have 1 per layer. Why is this so important? Because when you start to program, when you start to write your code for CUDA kernel code for convolution layer, for the sigmoid kind of layers and so on, you will need to to deal with these matrices and tensors. Okay, the tensors. So that's what this kind of intuition gives you. A very good intuition when you read the code. You will immediately be able to see what each level of the loop is doing and so on when you have this intuition. Okay, we also covered this one, but it's definitely worth talking about. Just quickly, review just to make sure that you really have the right intuition. By the way, this is the second material. Remember, when we talk about convolution, I said, hey, there's something that you should go back to to explain to your roommate during dinner, and if you can, explain that to your roommate and to the full satisfaction of your roommate, then you really understand it. So here, this is yet another one. Okay, this is another material that you should try to explain to your roommate during dinner. And if a roommate can fully understand it, then you fully understand it. Okay, so that's it's an invitation for you to to have a real technical conversation with your roommate. So let's say if we have something like 784 inputs, it's a kind of a small image with 784 pixels, and then 1,024 outputs, and so there are 1,024 categories that we're trying to classify that image into. Then, we're going to have, for that single layer, we're going to have 784 times 1,024 weight in the matrix. And that's a pretty big matrix, okay? And so that's why these things grow very fast. And then, the bias vector is 1,024 by 1, because we only need 1 for every output. So look at so if we look at the observational data, and we can actually, use the observational data and say, this is the data, and for each piece of image in the data, you have someone to tell you whether it's a dog, it's a cat, it's a something, and we want to be able to use that set of data to force the weights into the values that will produce the correct probability if we run that data set through the weights again, right? So that's what the training is all about. So with enough input data, we should be able to cover the real usage of this network in an arbitrary image in the future. And you should all realize by now that this is an impossible task, right? We already talked about the number of, the number of training inputs that you can collect is definitely much, much, much smaller than the entire possible space of images that you can have. I hope that first lecture already get you convinced. So it's all about finding the most important cases, okay? And then, finding the representative cases. Hopefully, one of the images will be able to represent a large class of possibilities as far as the extracted features of those images are concerned. So hopefully, you will have something like an image with a person in the image, and then your network should be able to generalize that input into person with a bigger size, smaller size in the picture, and slightly different positions in the picture, and then some slightly different orientation of the person, angle of the person in the picture. Hopefully, that picture will get you a kind of a representation for all those related pictures, so that each picture gives you a large number of training cases in the and so that you can adjust the weight accordingly. And that's really the foundation. That's really what the multi-layer perceptron is doing, because every layer is going to give you that little bit of data repositioning, so that hopefully many of these related pictures will eventually end up in the same place, okay? And then, we're good, okay? So all these things are statistical. So none of them are going to be perfect, but it's a matter of, whether they're going to be statistically better than the alternatives. So you're never going to be perfect, but hopefully you're going to be better than any other alternative means, including humans in the loop. Okay, so we are trying to outrun your friends, not the bear. Okay, the bear is impossible to outrun. So outrun your friends so that your friends will be eaten and you will survive, right? So that's, if you look at all the papers in these areas, they all say the same thing. I did better than that, right? And then I get, so the paper gets accepted. So, okay. So we already covered these, so I'm not going to spend much time on it. But there is a very, very important picture that you really have to keep in mind. We have the forward direction and we have the backward direction in our computation. The forward direction is very, very intuitive. You have the first layer, and then this is that sine function equivalent. Sigmoid is just a slightly smoother form of the sine function, and then you have the second linear layer, and then you have the sine, sort of the sine equivalent for the second layer, and then you have the argument. So this really is just a sort of a more abstract representation of the exclusive OR logic, right? So then in the end, you can calculate the error. The error is you take the probability for all the categories that this network generates, and then you compare that with the label. The label tells you this thing is a cat, right? So the probability should be 1 for the cat category and 0 for everything else. So you take that, your probability that you generate for every category, you subtract all zeros but only 1 in the cat category, you get a vector of differences. And then you take the square of that, of that vector, and then you divide by 2. That's mean square distance, right? That gives you the Cartesian distance between the two, and that gives you the error. Okay, that gives you kind of the error. So that's good. So you have a measure of error. So you can say, okay, how much effect does the input into this, the y that I generate, affect the error? So the y is my final outcome. Okay, the final outcome. And then, so the final outcome feeds into the error calculation, right? So whenever I change my outcome, I change the error, right? If I, make the probability of the cat higher and then, everything else lower, then I change the error value. So, I can calculate the derivative of my error with respect to that y, right? The faster the y changes, the faster the E will change. Yes? Yeah. Yeah. Okay. So let me just repeat the question. The question is, so what am I getting at? What I'm getting at is that to do the training, we first do the forward evaluation, and then get the output, calculate the error, and then calculate the derivative, and then go backwards and adjust all the weights. Exactly. That's exactly the process. Okay. So that's why any learning process requires inference. Okay. It always requires this forward evaluation. And this is a very, very general process for any kind of what we call the inverse solvers. Okay, the iterative inverse solvers. If you take any numerical classes for solving very large linear systems or differential equation systems, we always do something like this. We do the forward propagation, and then we do some adjustments to our solution, and according to the error, and then we keep doing this until we have a satisfactory answer. Okay, so we calculate that the derivative value, and then we can start to propagate back, because for this one, what we did was we look at y and say, oh, how quick is y is how much contribution is each y value to the error. So if I make some changes to the y, I will be able to either increase or decrease the error, right? So I want to adjust my y value to minimize my, to reduce the error, right? So that's what I'm going to do. And then I say, okay, so I know how much y value I'm going to need to want to change. But then you say, wait a minute. In order to change this y value, I actually need to to change the input to the sigmoid so that I can generate that y value, right? I can change the y value. So I can go back and say, in order to make so much change to that y value, how much do I need to change in terms of the input to the sigmoid value, which is the FC2 output? So the output of this function, how much of that function value needs to change in order for me to make the change to that y value, right? And then you go back and say, okay, now I know how much of the input, the FC2 value need to change in order to reduce that E. Now I can look at this function and say, how much of the, I need to adjust to the weight in order for the output to change in that direction I want, right? So this is why it's called backward propagation. You go from the very end, and then you say, this is how much my output needs to be adjusted. And then you go through each layer and say, this is how much the output of the layer needs to be adjusted. So let's look into the weight, let's look into the input, and see how much I need to adjust both of these. So after I adjusted the weights for this layer, now I have the input to that layer also changed. And I said, I need to make so much change to my input, but remember that input is always also the output of the previous layer. So you say, now I know how much of the output of that layer needs to be changed. So now I can figure out how much of the weight needs to change in that layer, and then how much of the input needs to be changed in that layer. So I just go layer by layer to figure out how I can adjust each of these weights. And you can think about this also like a carry propagation. You get some kind of sum, you generate carry to the next layer, and then you get the sum, you get the next layer. So these computations are exactly the same pattern, okay? So any question about the overall picture? This is extremely important because half of the people, who learn machine learning have no idea, okay? And, this is the computational angle. So in order to be able to go from the output, say, I know how much of the output needs to be changed, into the change of the weight and the input, I need to use chain rule, okay? Because I have, essentially I have the function, right? I know what the function is. I designed that function. So the function is known. So here I have the function FC2 is W2 times S1 plus W2. This is just that perceptron, right? Linear function, the simplest function you can find. Now, in order to, for us, we know how much S need to change at this point in order to push the error in the right direction, right? So then we can say, okay, I know how much of the S I need to change. So I can, I have the DSDE. So DSDE is how fast the output needs to change in order to get E to go in the right direction. So this is something that I'm going to be propagating from the back. Remember, I'm calculating DEDS as the outcome of this one. So I already have that by the time I get to this layer. But I need to get these two calculated. So I need to calculate this thing, and I need to calculate this thing so that I can generate the right values. So I'm going to go through that detail one more time to make sure that we're all good with the the calculation. So this is just a setup of the problem. And then we have two important models. Ideally, okay, this is going back to how we're going to calculate the error at the end. Okay, so remember, every image is going to want to push the weight in some direction, right? But not all the images are going to want to make adjustment to the weight the same way, right? Each image would adjust the weight in a different way. So if we just go ahead and readjust the weight after every image, it gets, we can get into some kind of, a very random input. Let's say if I want to move the exam date, okay, say, hey, class, I need to move the exam date. Which day will be the best? Each of you will have different constraints. Each one of you will want to move the exam date in a different way. We may never converge. So if everyone just wants to put in opinion and don't want to take anyone else's opinion, we're not going to be able to converge. And this is exactly what's happening in these math kind of things. The convergence requires you to be able to take multiple potentially conflicting directions and reconcile and get a reasonable direction that kind of take everyone's input into consideration. So that's why we have this process. So the simplest way is just gradient descent. And for every image, we read the input image into the input. We evaluate the network forward, okay, to the output. And then we compare the target label to the output. This is, I already explained this, right? We and calculate the error. And then we back propagate the error derivative to get the parameter updates in each layer. And then we adjust the parameters, essentially the weights and the biases in every layer. And then, by doing a little bit, so we calculate the difference vector that we want to do, but we don't fully adjust according to that particular image, because that image may have too much influence. So each image may change too much that we may never converge. So we multiply that with a little epsilon here to kind of mute the influence of each image, okay, a little bit to a very small amount. And so then essentially you repeat that process, and this is equivalent to having everyone to voice, okay, everyone to voice their input, and then I keep changing. After I listen to you, I change my date, and after I listen to you, I make another change to the date, and I may go all over the place just so that hopefully I would settle, right? So that's the sort of the basic approach. And then in reality, we actually don't do that, but I'll come back to this point very soon. So this slide is a very, very important slide for you to understand the real computation of derivatives, how we're going to calculate the derivatives. So we start with, so this is a single layer. If we can fully understand how we adjust the weights of a single layer and how we propagate what the input needs to change according to what the output needs to change, then we can understand every layer, right? We can just repeat that process. So this is a single layer, and the network function is this. So this is one of the perceptron layers, right? Perceptron layers. Weight times the input plus bias gives y. So this is one of the linear perceptron layers. So we can do a derivative of dy over dw. So this gives us the importance, right? The importance of w on the output. So, and this is a partial derivative. So we're going to be calculating the importance of every weight value for the output, right? So you can, you have so many weights, so you can have partial derivative. When you change each weight value, how does that weight change affect the output? So this is what the partial derivative is all about. So the partial derivative, can be evaluated fairly easily, and as we will see, and because this thing, remember, we have a w vector inner product with the x vector, right? X vector, to get that inner product value, right? Inner product value, and then we use the inner product value plus bias to get the output. So whenever we need, if we expand it out, this is one w element times one x element plus another w element times another x element, right? That's what inner product is about. So if I need to calculate the partial derivative of any particular weight element, I look at this whole expression. When I take the derivative, only that weight element is the variable. Anything else is a constant as far as the partial derivative is concerned, right? This is the whole point of taking the Calc 2 and so on, okay? When you take a partial derivative of one of the coordinate variables, every other coordinate should be viewed as a constant, right? So here, if I want to get the partial derivative of output based on a input, a weight, then only that weight element is treated as a variable, and everything else is a constant. So when I do the derivative, everything else becomes 0. Constant derivative is 0. And the only term that's left is going to be the w element times the x element that will be that should be multiplied to the w, right? So that x element becomes the derivative value, because constant times x derivative is just a constant. Okay, this is the basic polynomial derivative. So that's why when I need to calculate the partial derivative of output based on any weight value, it's going to be the x element that will be multiplied to the w value. Okay, so this gives us the partial derivative value that we're going to use in the chain rule. Okay, in the chain rule. Now, we can start with the error function. So the error function is half of the y minus t squared. So let's assume that if this y value feeds into the final outcome, so the derivative of the error the error, how y affects, of this layer affects the error is the derivative of e over, partial derivative of e over y. Again, if you think about this y, okay, this y is a vector, right? Y is a vector. So I can calculate the value of every y, okay, how important every y is for the error by just doing a derivative of this thing. And this is going to be, it's a simple polynomial expression. So 2 comes down, and then, so it's y minus t, and then this derivative itself is just 1, because this is a y variable right here. So the derivative is a very simple y minus t here. So this derivative gives us the relationship between the y value, a particular y value, and the output. And that y value is generated by the particular set of w and b inner product with x, right? So I can replace y with the function here, so I get wx plus b minus t. So this is actually that d e d t dy that I want to start with. Okay, I want to start with in terms of the importance of the output. So this is the anchor that I'm going to use to interrogate and to change the weight of the layer. Okay, so this is d e dy is the wx plus b minus t. So for every weight that I want to adjust, I do a partial derivative of the e over that weight value, which becomes the partial derivative of y, the output of the weight value, times the partial derivative of e over dy. This is just a chain rule, right? Chain rule where I take the dy, de, dw, and then I make it into the product of dy dw times de dy. Why is that? Because the first one I already know. I already know what de dy is. De dy is just the same, w times x plus b minus t. And I also already know that what dy dw is x. So the de dw is actually just the product of this, so it's actually just wx plus b minus t and times x. Remember, this is for every w element. You need to be able to change the w element value, right? The vector is an abstract concept, but in computation, you're going to need to change every element value when you adjust the values. So for every element value that you need to adjust, the amount of adjustment that you want to do is the weight, the value of that particular element, okay? And times so this is the inner product expression for the for the y, and then this is the particular x element that will be multiplied, okay, with the weight element. So this gives you essentially the direction that you want to give, you want to make the change to that w element, right? And then you subtract that, because this gives you the positive direction. Whenever you do this adjustment, your error value will change in the positive direction, and that will increase. So you don't want to do that. You want to subtract. Subtract, that gives you the negative direction for the error. And then you multiply this little epsilon to make sure that you don't make too much adjustment. So this gives you the total adjustment value. This is called the gradient weight update expression. And this, hopefully, for every image, you will be able to make the correct adjustment to every weight element. And you generate the expression for the input based on, also based on this. And then you can go to the next layer, right? So this is the practical view of the weight adjustment in the training process. So now when you look at this picture, it should become, very clear to you that, when I want to calculate the weight update for each layer, I need to get, the value that is propagated gradient from the backward pass, and x is the element that I'm going to get from the input pass, from the input direction. And that gives me the entire computation picture. And you will see that we're truly going to be going, layer by layer backwards to be able to calculate all the adjustments. So, what is a fully connected, gradient? Essentially, this is a picture that I show that, you have these FC1. FC is the function output, and then you have all these, output values. It's a vector. That's the Y. And then you have the weights. You have the weight matrix, and you have the input X values. So this is really a matrix vector multiplication that gives you all the inner products that you need in order to calculate the function value, right? And the FC1, the function itself, is really the inner product, okay? The inner product of all the sum of inner product sum of all the relevant W values and the X values. So it's really just one of these rows of W and the vector X, okay? And then so when you do the derivative, and you're going to have the derivative of this, and then this is really, this is just what's being propagated from the previous stage, and then x1 is really just you take this inner product, and then you only hold one of the W values as a variable, and then you will get the x1j for that particular weight. So this gives you the partial derivative of E over a particular weight value, okay? Just a summary, but computation-wise, this is the view that we're going to use. So it actually can be really, really slow and also really unstable if we go and try to adjust the weight at every image, okay, after every image. So that's why based on the statistical properties, we don't go and adjust the weights immediately after every image. We actually have a concept of training epoch. Epoch ideally is just one pass through all the training images. Okay, you take a pass through all the training images, and for through the image, you evaluate forward to get Y for every image, right? For every image, and then you compute the error, and then back propagate all the parameter values, okay, all the changes that you want to make to the parameter values. But you don't immediately make the change, okay? Because if you make the change, that change is going to be reflected in the next, for the next image. So you don't make the change, you still use the same weights for the next image, but you keep accumulating the delta that you want to, that every image wants to make, okay, to the weights. So if you have 1,000 images, the first image, you have all the adjustments you want to make to the weights and the biases, right? So you don't do anything, you just keep accumulating for every image. So by the end of the 1,000 images, you have accumulated all the changes that you want to make for every weight. And then you take that, and then you do the epsilon thing, and then you do the adjustment. So essentially, you're kind of adding up all the inputs from everyone, which way, you want to change. Someone wants to change in this way, someone wants to change this way. You may end up changing nothing, right, by accumulating, rather than doing the change and then try to come back and so on. So this is called, batched stochastic gradient descent. So essentially, you take a whole batch, and then, of the training input, you figure out the consensus or accumulated, compromised, adjustment that all these inputs want to make to the weights, and then you make that change at the end of the pass through all the images. So that's called one epoch. Okay, so we also have the concept of mini batch, because if you do this kind of training, every time when you make that adjustment to the weight, you actually need to go through another iteration and another iteration until we converge, right? Because what happens is that you go through the whole epoch, and you make the you make the changes to your weights. If you run the same test images through, you may or may not have made enough adjustment to get the correct outcome, right? So that's why you need to do another iteration, and this plan is based on the adjusted weights, and hopefully the adjusted weights will kind of just slowly converge into the weights that you want them to be for this training set. So oftentimes this will take a large number of iterations so that the weights will be adjusted by a small amount in every iteration through the entire data set. And now you see why the training process can be very slow, right? If you have millions and millions of training images, and you need to go through each task, you need to go through millions of these training images, and then you need to do the the iterations, right? So this can be an extremely costly process. That's why in practice, people don't really do entire set of entire tasks through all the training images. We do what we call the mini batching. Okay, the mini batching. So essentially, we take a kind of a mini, a small subset, smaller subset of the image, and oftentimes we use sampling, to take from the image. So we form a small subset, and then we go through the small subset exactly the same way as we would for the entire batch in the previous approach. And then we identified that the changes we want to make to the weights, we make to the weights, and then we sample. We can sample again and take another subset, and then we do the same thing. And hopefully the subsets are representative enough of the entire training set that each step will have the same similar adjustments that we will be making to the weights as if we look at the entire training set. So this is called mini batching, okay? And this is a compromise between the accuracy and parallelism, right? So we're going to save some computational cost, right? But hopefully we didn't sacrifice too much about the accuracy. So if the samples are representative enough, okay. So you will see this concept of batch number, okay, the batch number in your training data. So one of the important decision we need to make is, when are we done? Okay, and essentially this is the ultimate question, right? So in every education, for example, all of you are trying to finish your degree. So when are you done? Okay, and what we say is you take enough credit hours and then you're done, right? Or we can do a different approach. We can say every year we have all of you to take an exam. Okay, we test you on everything you learned in the ECE or CS curriculum. Okay, every year. If you pass the test, you graduate. If you don't pass the test, iterate. Right? It's a different approach. And hopefully everyone will converge, right? Everyone at some point will pass all the tests and then graduate. Some of you may benefit by graduating in 1 year. Some of you will. Okay, some of you will be able to pass all the tests in 1 year. And some of you may spend the rest of your life here, who knows, right? So that's why we have this concept of, when do we have, when is it good enough for us to say this thing has been trained and it can go into industry and make billions of dollars and come back and donate to the next ECE building. Okay, so beneath you, right? So, by the way, when we have this new ECE building, I have been saying this for the past 30 years. When you go out to industry, you make millions and billions of dollars, come back and donate to the new ECE building. I was kind of joking, but it turned out that more than 20 of my previous students came back and donated when we built the new ECE building. So you never know, okay? When you have become a billionaire, you can, if you have to choose between what I said about perceptrons and training and so on versus come back and donate, it could be a hard decision to make. Which one I prefer you to remember. Okay, so that's a joke. So when is training done? You can just essentially take the loss function, which is the error, okay, which is the error function value at the end, and you will see hopefully that with every iteration, either through the entire training set or the mini batches, right, the iterations, and you will see that the error function hopefully will keep going down until the error becomes so small that you say, okay, this thing is very, very good. The problem is when you converge on the training set, you may not be able to have improved real usage. When you have a set of data, right, a real world input into this trained model, they may or may not be trained for that kind of input, right? So you can easily have a situation like this. You can keep improving on the training set, but when you use the model in reality, that model may not be able to further improve beyond a certain point because you're specializing this training, this model to the training data. And you specialize it so much, it did so well on this one, that in reality, when the real data comes in that covers a lot of the things that you didn't have in the training set, you specialize yourself so much that you may even begin to do worse, right? So, this is the reason why, we need to, at some point determine when the training is done, whether it's good enough. Don't train it. This is called overtraining. And the network can become too good in classifying the training inputs that it may actually do worse in the real world, okay? And we all know that that's also part of the education process. We can over-specialize you, when I teach these classes. And then you may actually do super well in some of these classes, and you end up doing worse in the real world. It can happen, okay? So these are the real problems that we need to, always be vigilant about when we do anything, right? Okay, now, so, this is a kind of a visual, illustration of, how things get over trained. So, for example, if you have some training data like this, and you say, okay, I'd like to, figure out a function that would represent, that will generate the data points that are represented by these samples. So you can, try to fit it with a linear function. You can try to fit it with a quadratic function. Who said that? Quadratic. Thank you. So then you can, use a cube function, right? So the thing is, when you start to, you can actually get even better fit with a cube function because the curvature and so on can be more, dramatic in these places. But the problem is when you bring in another, the polynomial the term for the quadruple term, for the cube term, you also start to introduce some of these, ups and downs because of the cube function characteristic. So you always have the potential of fitting the sample things better, but by bringing in some ridiculous things in elsewhere to be able to get your results better here. Okay, so that's why when you do more and more iterations, you can actually begin to have the same effect as getting more and more terms in your Taylor series expansion of these functions but then you start to have these kind of, an unwanted behavior in the data points that you have not seen. So that's why, you start to have this kind of, overtrained network where the network is too good at the training data and the new inputs can actually have unpredictable output effects. So this is the reason why when Google and my friend Elon Musk, Tesla, try to do these self-driving cars, you know what? They only use the training data to a certain degree, and at some point they start to get the drivers to take out the car to all kinds of situations. And in fact, it's kind of entertaining to watch. You will see the Google car in Mountain View, and then they will come out at different traffic times, different weather, different. They really try to capture all the realistic driving variation conditions. At some point, they no longer rely on the training data they have for these models. They actually take the car out because they realize that they can overtrain their models. Okay. So there is something called the no free lunch theorem. I don't teach machine learning, and I don't feel I'm an expert, but this is something that you actually need to also realize for computational reasons. No classification algorithm has the same error rate. Every classification algorithm has the same error rate when the previously unobserved inputs when averaged over all the possible input generating distributions. So essentially, if you have a model, okay, a model, and it doesn't matter which model you use. When you train with a particular set of training data, okay, and then you apply unobserved data, right? The real world, the real input has some unobserved input, and it turns out that no matter how clever you are, in the end you will have the same average error rate across all these models. So this is a statistical proof that people make. It's called the no free lunch theorem. So what that means is that it's kind of hopeless trying to be clever about your model. Okay, so you really need to to work on your training input set, and by keep improving your model, you will not be able to to do better on average, okay, on anything that you did not include in your training input set. And unfortunately, if you use try to cover all possible cases in your training input set, there'll be too much input, okay? And then what, you can actually have all kinds of problems in terms of convergence and so on. So that's why we begin to see models that have more and more and more submodels and all these things, because we train these submodels with different kind of types of inputs, and hopefully collectively they will be able to cover the the unobserved situations better and better, because we have less and less unobserved situations when we feed the different scenarios into these models. Okay, so that's why more and more of these things are getting bigger. You have models with hundreds of stages, and you have different feeding patterns and so on, and hopefully those things are trained by different sections of the input, and you use tremendous training set to be able to train those models. Okay. So here we are. We have classification, and this is a simple function, and we have a perceptron right here, and it's actually a really, really powerful thing, especially you have multiple layers. And then we use chain rule to compute these parameter updates through the process. And you really should go back and use that simple, example to go through that backward propagation process, and so that you have very concrete understanding of it. And then we use stochastic gradient descent by doing mini batching, right, of epochs and so on, to be able to adjust the weights in a way that it will converge. Okay, so this brings us to what I really should have started with today. So we're slightly behind. But I think it's okay because you know what, it's better to be one lecture behind rather than having many of you struggling trying to understand the code and without the right kind of intuition about the code. So this is the beginning of introduction to neural nets. Okay, so that we're going to begin to to have you to work on the neural network layers and how you can use GPUs to be able to do this. So this is a historical slide where we in the computer vision field we have decades of work to sort of in terms of trying to design computer vision algorithms to be able to recognize objects automatically. And in the field we have a particular competition, and so this is the ImageNet competition, and so over the years we have all teams from the country to come and compete. And this ImageNet is put together by a former faculty member here, Fei-Fei, I think Fei-Fei Li. So she moved to Stanford, after she put together. I think then she put together the ImageNet at Stanford. So she essentially is a collection of input images. And then, the teams come and compete and then see, how well they do in terms of the accuracy of classification. And then, so in 2010, you have all these, image, computer vision groups coming and compete, and their accuracy of classification range from 72% or so down to something like 2%. Okay. And so obviously this is quite good, and this is equivalent to ice skating and you fell on the ice 3 times or something. You get that kind of score. Okay, so this this is the range of of the algorithms that people use, and they have handcrafted features trying to to match into the picture, and then try templates and so on. And 2011 you have these competitions, and then you have 2012. 2012 was actually interesting. So what happened was that we started to teach the GPU programming class here in Illinois in 2007, January 2007. And then in year of 2010, Professor Mashovis, Andreas Mashovis, call me from Toronto and say, hey, you know what, we want to offer the GPU programming class to the grad students, and can I use your material? I said, sure. And Andreas, I knew him when he was a grad student at Wisconsin, so of course. So he took the GPU, the early 408 material, and offered that to the Toronto grad students. And some of the grad students in that class were, the computer vision students. One of them is Alex, and the author of AlexNet. So basically, that was their term project for the class. And then 2 years later, they used the neural net implementation that they did in the class, okay, and participated in the competition and trained the neural net with 1.2 million images using GPUs, okay. And then they went and did the competition, and they won by a big margin over all the other teams. But these are the two only teams that use GPUs. They're one of the two teams that only teams using GPUs, and the rest were using the features. After this competition, the next year, everyone switched. Everyone started to use the neural net. And the rest of this history we have these improvements. Yes. Yeah, exactly. Yeah. So this is now we're at somewhere around 95% for the ImageNet competition. It doesn't mean that these things are going to be 95% in every use, but for the data set that for the ImageNet, we're getting to over 95%. Accuracy and so on in the okay, so we can start with multi-layer perceptron. Okay, so we have talked about perceptron, right? So, intuitively, this is a very simple application of the perceptron, multi-layer perceptron. We have all these pixels, right? The images are pixels into the system, and then we have the classifications in output. So this is perfect, as a classification with perceptron classification problem. So let's say we have 200 and 200. 250 by 250 pixel images. And so essentially we take the 250 by 250, it's about 62K or so images, pixels, and we linearize it into a 1D array. So these are the X values, okay, all the X values, about 62K X values. And then, we have, the output will be, all the things that we want to, classification or all the, different classes of, objects that we want to be able to identify. And so the question is, how many of these, multiple hidden layers do we need? How entangled these things are, how many layers we need to use to be able to entangle them, disentangle them. And so one of the problems is immediately that we have, way too many weights. And we have, it will be computational and memory intensive, okay? Because you remember, we need to have the number of inputs times the number of outputs weights, right? To be able to do one layer, and then we have all these, multiple layers, right? So it's going to be extremely, data intensive in terms of weights. And when we train these weights, there's actually a potentially a problem. When we train these weights, we have so many ways to adjust that we can easily get into the situation where we can never converge. Okay, we may never converge in that in the kind of the. So this gives us sort of an interesting change from the all connected layers to convolution layers. Okay, we still use all connected layers, on a need basis. But we usually use them later on for exactly the reason that I just talked about. So let's go through the kind of the, how we got to get there, okay? So this is a review picture of 2D convolution, right? So this picture should be very familiar to you. We have a input image, and then we have a filter. We have a, the convolution mask for filter, right? So this is a 5x5 filter. So we can, take the region, in order to generate the output, to generate the output for this thing, okay, for this point, we go to the corresponding point in the input, and we do the 5x5 region around it, and we take the 5x5 region, we use the mask with the mask value for the inner product, and then we generate the output, all the products, and then we sum them into the final inner product value, right? So this was a slide from the convolution review. So on the left, I showed the all connected, fully connected, perceptron. So we have inputs, we have all these inputs, and we need to have as many input value as as many weights as the number of inputs, and every input needs to have this weight coefficient. And we generate the inner product for every for all the involving all the inputs, and then we add the bias and we generate the output, right? So this becomes too expensive. So what we do is this: we say, okay, instead of having everyone to participate, let's have subgroups. Okay, we have a subgroup discussion about when the exam date should be, and subgroup discussed when the exam date will be. So that essentially we, in order to generate the output, we're going to actually take the a sub area in the input image, use a convolution mask to generate an inner product, and then we generate output. But instead of generating one output out of the fully connected layer here, we will be generating subgroup outputs, right? So we'll be generating multiple of these subgroup outputs out of the convolution. So, you generate one value here with lots of weights. You generate a collection of output based on much smaller number of weights. Okay, so that's the kind of the comparison. So, essentially, the very desirable, property or undesirable property of the fully connected layer is that when we start to have bigger and bigger pictures, right? When we start to have bigger and bigger pictures, we will need to have bigger and bigger weight matrices. So the system does not handle big inputs very well because you need to have very big input weights. And so if you train the system with some kind of picture size and you try to apply it to a different picture size, you're in serious trouble, right? You need to retrain it with all these the increased number of weights. But here we use the same number of weights for all these subgroups. So when we use a bigger picture as the input, all we do is we generate more subgroup outputs, but the weights remain the same. Okay, so this is a more scalable approach in terms of the input image size. So we can use the same trained weights, right, for bigger, smaller images by just generating more or less subgroups, okay, of output. So this gives us the ability to deal with variable size inputs, and so we have the variant observations of the same kind of thing. And so, for example, we could have audio recording of different lengths, right? Or image with more or fewer pixels. And so this approach will allow us to be able to deal with that variation using the same model, right? Otherwise, we will not be able to do this. So the examples of these convolution inputs are audio waveforms forms in the single kind of a 1D is audio audio waveform samples. Model channel will be kind of a skeleton animation data, or 1D joint angles for each joint and so on. So that would be the 1D input, and then 2D will be Fourier transform audio data to give you that space-time data. Or so in the multi-channel you can have the color image data to 2D for RGB, and then 3D could be volumetric data like for medical imaging. And then, for multi-channel, you can have color video, and so two-dimensional data across 1D time for RGB channels. So you have 1D, 2D, 3D data, and in every case, if you want to use, multi-level perceptrons, you're going to just linearize the 2D or 3D into this big vector, and just feed that into the perceptron. And here, if we use, convolution, we keep the original structure and then just use the 2D convolution or 3D convolution to generate those kind of the subgroup outputs. So we are at the top of the hour. So we're going to have the exam on Tuesday, so we're not going to have class. Okay, and on Thursday, I'm going to start with this slide and talk about the convolution layer, the subsampling layer, and so on in terms of sequential computation. And you will begin to receive the project files that include the sequential implementation. So you will need to begin to work on the sequential implementation, working towards the kernels for these layers. Okay? So I'm going to be traveling on Tuesday, so good luck on your exam. Okay? Study hard, good luck on your exam, and I'll see you on Thursday.